Alright, so I'm going to be covering Chapter 11 from TRO for General Chemistry, Chem 150 at Crafton Hills College. I'll be covering Chapter 11.1 to 11.7. 11.8 will be for another time. So we're going to talk about molecular shapes. We're going to talk about valence bond theory and hybridization and all that fun stuff. All I'm doing in this lecture is presenting material. I'll be working problems in a separate recording. Okay, so in the previous chapter we talked about ionic bonding and covalent bonding, which are two bonding models. Remember, models only give us an approximation of real life, and they usually do an okay job, but sometimes we encounter situations that covalent and ionic bonding can't explain. For example, we generally have the octet rule, which is guided by Lewis structures and wanting you have your shells full, S and P. But sometimes we break the octet rule. And we went over that in Chapter 10, but we didn't say why are we breaking that rule? What is our justification? What are the theories behind why we break that rule? So we're going to go into that in Chapter 11. Okay, so when we talk about Lewis structures like we did in the previous chapter, Lewis structures shows you the connections between your atoms in the molecule, but it can't give you the shape. And molecules exist in 3 dimensions. They don't exist on a flat piece of paper. So we use Lewis structures to help us figure out what is the 3-dimensional shape. And sometimes this can be hard to visualize. So I'm going to refer you guys to a couple of videos that are really good with visualizing these 3D structures. So what determines the shape of a molecule in 3 dimensions? And the idea behind what determines the shape is that electrons are contained in the bonds. And since they're all negatively charged, they're going to repel each other. Because like charges repel each other, opposite charges attract. That's the basis of ionic bonding. You have oppositely charged particles that are attracted. But if they're the same charge, like all these electrons in all these bonds, or if they're lone pair, same thing, they will repel each other because they're negatively charged. So since they do repel each other, we assume that these pairs of electrons contained in bonds, or non-bonding pairs, they want to be as far apart from each other as possible. That is the basis of the VSEPR theory, valence shell electron pair repulsion. So when we talk about electrons and electrons that repel each other, we have to keep in mind certain locations are containing certain electrons, and these are called electron groups. Electron groups are locations where you're going to find your electrons in a bond. Now the thing that's tricky about counting electron groups, we can also call them VSEPR groups, is that a single bond is a single electron group. A double bond is a single electron group because it's a single location, just very high electron density with a double bond. A lone pair is also an electron group, and it will repel bonds because it is also negatively charged. So in my example here, I have my imaginary generic compound here, A bonding with 3 Bs. We always look at the central atom and how many electron groups does it have. We don't care about electron groups in the outermost atoms. We just care about the central atom, because that's what determines the shape. So if we look at the central atom, which is here A, he has 4 electron groups. 1 electron group for the lone pair, 1 electron group for single bond, double bond. So a total of 4 electron groups. 1, 2, 3, 4. Okay, let's see if I can bring up my highlighter here. There we go. So 1 electron group, 2 electron groups, 3 electron groups, 4 electron groups. Total of 4 electron groups around our central atom. So we can imagine these bonds repelling each other like if you had a cluster of balloons. So we have a balloon analogy to help illustrate if we had 2 electron groups, like these guys here. This is how the balloons would position themselves, pointing in opposite directions. That is a linear orientation. The balloons make a line. If you have 3 balloons, they'll arrange themselves this way. So imagine each balloon is an electron group. And they'll arrange themselves this way, and then if you have 4 of the balloons, they'll look like this. This will help to visualize how these bonds are repelling each other and what shape they have when they repel each other. All right, so the next few slides will show the geometries for if you have 2 through 6 electron groups. Keep in mind, if you have 5 or 6 electron groups, you are breaking the octet rule, okay? So 2 through 4 electron groups, those are all following the octet rule. But if you have 5 or 6 electron groups, you're breaking that, okay? So the way you need to figure out your geometry is you need to start with drawing the Lewis structure. Because when you draw the Lewis structure, that gives you how many lone pairs of electrons you have on your central atom and how many bonds are present, single, double, and triple. And we want to know how many of these are on our central atom. Remember, we only care about the central atom. This part is potentially confusing. Okay. So here's our 6 main types of shapes, depending on how many electron groups you have. Remember, these electron groups include the fact we have lone pairs as an electron group. Okay. So if we have 2 electron groups, we have a linear molecule, and our bond angle is 180 degrees. That means the farthest apart these bonds can get from each other is 180 degrees. That's what we call the bond angle. If you have 3 electron groups, this is called trigonal planar, and your bond angle is 120 degrees. If we have 4 electron groups, we have a tetrahedral shape, and our bond angle is 109.5. We have 5 electron groups around our central atom. Now we're breaking the octet rule. We have the shape called trigonal bipyramidal. And we have 2 possible bond angles. 120 degrees for the equatorial positions. We'll go into that more later. And then 90 degrees between the equatorial and axial positions. Again, we'll go over this stuff later. But these are our bond angles that we get with these shapes. And then if we have 6 electron groups around our central atom, we have an octahedral shape. And all the bond angles are 90 degrees. I'll be going over example 11.1 in your textbook in a separate YouTube lecture. So these are your electron domain geometries that accounts for all your electron groups, including your lone pair electrons. But we have a separate group of geometries that are called molecular geometries. When we look at molecular geometries, we ignore the lone pair electrons. So in the previous slide here, we're including all the lone pair electrons in the electron groups. This is electron group geometry. It accounts for everything, bonds and lone pair. For molecular geometry, you ignore the lone pair and just look at the shape of the bonds. There's 2 types of geometries going here, electron group geometry and molecular geometry. So let's go through all of our geometries here. If we have 2 electron groups, we have a linear shape. So the bonds are forming a line. And this is called linear with 180 degrees between the bonds. That's our bond angle. And there's a YouTube video here that will show, let's see if this works. No, this will not work. Okay, there's a YouTube video you can look at later. If you follow the link, you'll see the linear shape for CO2 molecule. Now, if you have 3 electron groups, there are 2 possible molecular geometries. If all your electron groups are bonds, you have trigonal planar, like with sulfur trioxide. If we have 1 lone pair and 2 bonds, for a total of 3 electron groups, our electron group geometry is trigonal planar, but our molecular geometry is bent or angular. So then a good example here is SO2, and this is a YouTube link if you want to look at an SO2 molecule. Alright, so if you have 4 electron groups, there are 3 possible molecular geometries, depending on if you have all bonds, 1 lone pair, or 2 lone pair. If all your electron groups are bonds, you have a tetrahedral arrangement. If you have 1 non-bonding pair and 3 bonds, you're trigonal pyramidal. Good example of that is ammonia. And then if you're bent or angular, that means you have 2 pairs of non-bonding electrons and 2 bonds. Anyway, there's links here you can look at what these shapes look like. Okay. So bond angles change slightly depending on if all your electron groups are bonds or if you have a lone pair or 2 lone pair. Lone pair electrons repel more than bonds, and they take up more space. So this will affect your bond angle. So if we have methane here with carbon as our central atom, and there's 109.5 degrees between each CH bond, that's your tetrahedral shape. You have a tetrahedral electron group geometry and tetrahedral molecular geometry. For ammonia over here in the middle, let me bring up my pointer again. For ammonia here, this lone pair is pushing away the bonds, and it compresses the bond angle. So our bond angle for ammonia is 107. This is measured in the laboratory. There's no way you can figure that out on your own. This is a measurement. For water, we have 2 lone pairs and 2 bonds. So the 2 lone pairs compress the bond angles even more, so now your bond angle is 104.5. You don't need to remember these compressed bond angles. You just need to remember your 109.5. That's what you're going to see the most. Multiple bonds are also more repelling than single bonds, and this will also compress bond angles. So if I have 3 electron groups on my central carbon atom here, and this is phosgene, your idealized bond angle would be 120, but this double bond is pushing away the single bonds. So you have a larger bond angle here between the double and single bond, and a smaller bond angle between the 2 single bonds, because this bond angle here is being compressed. Because this double bond is more repulsive, because this double bond contains 4 electrons, the single bonds only contain 2 electrons. So it changes your bond angles. Again, you cannot calculate this, so don't worry about these exact numbers. Just know that with your trigonal planar arrangement, you will typically have a bond angle of 120 degrees. So now we're going to go into the shapes that break the octet rule. Because remember, if your central atom is row 3 and below, you could break the octet rule, because they can access those empty d orbitals to make more bonds that we talked about in the last chapter. So we have new domains that you will not have seen in your intro class, because you don't go over this in your intro class. In fact, it would be very unusual if you did. So if you have 5 electron groups, your electron group geometry is trigonal bipyramidal. And if you have 6 electron groups, you have octahedral. Well, what if some of those electron groups are a lone pair? We get extra shapes. But first we'll start with our basic trigonal bipyramidal shape. There are 2 types of positions. There's the equatorial position, where you have 3 lying on a plane here. Now what do I do? You coughed. Okay. So I have 3 equatorial positions that are 120 degrees apart, and then you have these axial positions that form a line. So in your equatorial positions, you have a bond angle of 120. With the axial position, if you just go axial-axial, this is 180, but axial to equatorial, this is 90 degrees. Now we get new shapes if we have lone pairs instead of bonds in any of these positions. The thing to remember is if we have a lone pair present in our molecule, they will always occupy an equatorial position. This is what's always been observed. So now we get some new shapes. If we have no lone pairs, the electron group geometry and molecular geometry are the same, trigonal bipyramidal. If you have 1 lone pair, that shape is called seesaw. If you have 2 lone pairs, that shape is called T-shaped. If you have 3 lone pairs, all your equatorial positions are used up by lone pairs. Then you only have those axial positions containing bonds. Now you've got a linear molecule. So if you follow this link, there's a really good YouTube video by Tyler DeWitt that goes over these additional shapes, and he's got some nice tinker toys that he can help you visualize these different shapes and why they're called what they're called. Why seesaw is called seesaw, why T-shape is called T-shape. Okay, T-shaped is because it makes the shape of a T. That's basically what it is. So anyway, if you watch this Tyler DeWitt video, it's about 15 minutes. He has a really good Tinker Toys to show you what these shapes look like in 3 dimensions. Okay, so that was for 5 electron groups. Now we're going to go over our shapes for 6 electron groups. Again, we're breaking the octet rule. If all your electron groups are bonds, your electron group geometry and your molecular geometry are the same, octahedral. If you have one lone pair, for one of your positions, you have what's called square pyramidal. If you have 2 lone pairs, you have square planar. And this is the only shapes that have been observed for 6 electron groups. And again, there's a YouTube link here. You can watch another Tyler DeWitt video explaining these different shapes and why they're called what they are. I'll be going over examples 11.2 and 11.3 in your book in the next video. Okay, so what if we have molecules with more than one central atom? Well, what you do is you look at one central atom at a time and predict the geometry around each central atom. And 11.4 is on this topic of larger molecules with more than one central atom. Again, I'm going to refer you to the next video. Okay, so why are we doing all this? It's exhausting. We do this because we need to figure out if our molecule is polar or not. In the previous chapter, we went over polar bonds. Now we're going to go into polar molecules. Because you can have a polar bond in a molecule, but if your molecule is perfectly symmetrical, again, we need the geometry of the molecule for that. What is its shape? You can have a non-polar molecule with polar bonds. So we need to walk through, why are we doing this? We're doing this to find out, do we have a polar molecule? And that's important because if we have a polar molecule, that affects all kinds of things, like boiling point, melting point, viscosity. It affects a lot of things. Will something dissolve in water or not dissolve in water? It determines physical behavior and chemical behavior. So we want to be able to know, why is this molecule polar? Well, because of the shape, and do we have a polar bond or not? And that's why we're doing this. So let's go into molecular shapes and how they relate to polarity. Okay, so what we need to know about those polar bonds we talked about in Chapter 10 is polar bonds are vector quantities. That means they have magnitude and direction. So if you have polar bonds pointing in the opposite direction, they cancel out. So we need to know, is our molecule symmetrical? If it is symmetrical, the dipoles all cancel each other out, and the molecule is nonpolar overall. And you have a symmetrical distribution of charge in your molecule. That's why we need to know the shape. It will tell us if our molecule is polar or not. And again, it affects all kinds of things. Melting point, boiling point, chemical behavior. Has a lot of real-world consequences. So here's some examples of polar bonds that cancel out. Here we have carbon dioxide. This is a perfectly symmetrical molecule. Okay, I have 2 electron groups on my central atom, so I have a linear arrangement. I have a carbon-oxygen double bond on both sides, so I have 2 polar bonds of equal magnitude pointing in opposite directions. It's like 2 children pulling on a string with equal weight. The string doesn't move, right? So you're nonpolar. The dipoles cancel. Here's another example, BF3, boron trifluoride. It has polar bonds, but it's a nonpolar molecule because trigonal planar is a perfectly symmetrical shape, and all the dipoles cancel out. This is a nonpolar molecule. In this case, we have 3 children pulling on a string with equal force. The string doesn't move. Our next example is germanium dichloride. He has polar bonds, and it's not symmetrical because we've got 2 chlorines, one here and one here, and then we've got a double bond here. So we're going to use this analogy with the children on the string, only now one child has let go of her string. Now the dipole moments do not cancel, and we have a polar molecule. Another example of a polar molecule is water. Water is not symmetrical because I've got 2 hydrogen bonds here and here, and 2 lone pairs I'm imagining here and here. And so if it's symmetrical, I have to be able to cut it in every direction, and it's the same on each side. And I can't do that for water. If I cut it vertically, it's the same on each side, but what if I cut it horizontally? Now it's not the same. You have to be able to cut it in any direction for it to be symmetrical. So water is not symmetrical. I've got lone pair electrons here and here. I've got bonds here and here. It is not symmetrical. This is a polar molecule. Water has a slight negative end on the oxygen side and a slight positive end on the hydrogen side. Okay, so if you want to figure out if a molecule is polar or not, you have to ask yourself a series of questions. First of all, is it covalent or ionic? If it's ionic, you don't care about polar. It's ionic. It's a different ball of wax. But if you're covalent, you keep going. Are the bonds polar? If the bonds are not polar, you have a nonpolar molecule. Like, for example, every bond in an organic, in a hydrocarbon, if you have an organic compound with just carbon and hydrogen, those are all nonpolar bonds. Those are all nonpolar molecules. They don't dissolve in water because water is polar. Fats and oils are not. They're all carbon-hydrogen bonds. So if your bonds are polar, you have to ask yourself another question. Is the molecule symmetrical? So if you have polar bonds and you are symmetrical, you're nonpolar because all your bonds are canceling each other out because they have magnitude and direction. But if you have polar bonds and it's not symmetrical, you have a polar molecule like water or ammonia. Anyway, I'll go over 11.5 in the next lecture. You have one thing to remember is that if you have different atoms attached to your central atom, they'll have different bond polarities. They'll have different magnitudes. So there has to be the same bond, the same atoms on those bonds to have the same magnitude of dipole to cancel out. So if you have 4 atoms on your central atoms, you've got a tetrahedral shape. If all those 4 atoms are the same, they all cancel. But if you have different atoms, they won't cancel. Okay, so that's it on molecular polarity. So we're going to move on now to a new topic. This is section weighted shapes, weighted polarity. Now we're going to do valence bond theory. Okay, so we're going to go into some new bond theories now that you haven't seen before. We've talked about covalent bonding and ionic bonding. And these are 2 models, 2 bonding theories. We're going to learn some more because they're going to help us to explain why are we breaking that octet rule. Well, we're going to find out why and how that happens. So we have 3 more theories, bonding theories, we're going to go over in this class. Molecular orbital theory, we'll go over that after exam 3. Don't worry about that for today and tomorrow. Just worry about the first 2, valence bond theory and hybrid orbital theory. Those will be on the next exam. Molecular orbital theory, we'll do that next week. But each of these theories explains chemical behavior our other bonding models don't explain. Okay, first we're going to go over valence bond theory. The idea here is when 2 atoms come together to form a bond, the orbitals overlap each other, and it's that overlap that forms the bond. So in my example here, I have 2 hydrogen atoms. They each have a 1s electron. They come together, and whether you have this overlapping of orbitals, that's your bond. That's your covalent bond. So we have overlapping valence orbitals that form bonds. That's the basis of valence bond theory, because now you have a shared space where those electrons can hang out. In my example over here, I have hydrogen chloride. Here's my hydrogen with its 1s electron. In chlorine, he has 1 unpaired electron in his 3p orbital. Remember, the p orbitals are bow-shaped. So your overlap looks like this, and there's our bond. Remember these bonds that we represent with lines? Bonds aren't really sticks. They're a shared space between atoms. Okay, my next example is a chlorine-chlorine bond with molecular chlorine. Again, each valence electron is in a 3p orbital. So these bow tie shaped orbitals overlap here, and there's my bond. There's my shared space. So that's valence bond theory. Overlapping valence orbitals, so you have a shared space. Sorry. So we need to remember that atoms can't get too close to each other because then the nuclei will repel each other. And if they're too far apart, well, you don't have a bond. So you have to find a happy medium between where you have a shared space to share your electrons without getting too close. So there's a balance between attractive and repulsive forces that determines what's the length of your bond. So now we're going to put a couple ideas together. We're going to put together the idea of Vesper theory and the shapes of these orbitals and the orbital overlaps. We're going to put these together, two ideas together, to form a new bonding theory. So what we're talking about when we combine Vesper theory and these shapes of atomic orbitals, the answer is we're going to have hybrid orbitals. We're going to mix orbitals together to make a new space. Think of it as knocking down walls in a house to make a new room. That new room is your shared space. And these are your hybrid orbitals. So hybrid orbitals are formed by mixing atomic orbitals to make a new space. Remember, orbitals are just regions of space where you're likely to find your electron. And when you make these new hybrid orbitals, they're all going to have the same energy. So they're called degenerate orbitals when they have the same energy. So you don't change how many orbitals are available, you're just changing the shape. So if you mix two orbitals, you're going to create two hybrid orbitals. If you mix three orbitals, you create three hybrids, and so on. You're not changing the number of orbitals, you're just changing the space, you're changing the shape. Again, it's like knocking down a wall in a house to make a new space. So here's our first type of orbital hybridization. And this explains why we have less than an octet in beryllium and boron, for example. Here with beryllium, we see sp hybridization. That means we're mixing one s and one p orbital to make a hybrid orbital. It's called sp. So here's my orbital diagram for beryllium. He's got 4 electrons. I got 4 arrows. So what beryllium's going to do, he's going to promote one of those electrons from 2s into 2p. Then he's going to blend these two orbitals together, the 1s and the 1p. And now I've got I've knocked down the walls in my house to make new shapes. These are now sp orbitals. I'm mixing my orbitals. Now I can make 2 bonds, one here and one here. I'm going to leave these 2 p orbitals empty. I'm not going to hybridize those because I don't need them. Okay, now I can make a compound like beryllium difluoride, which does exist, and this is why. Because we're mixing orbitals to make hybrids. And now we can ignore these empty 2p orbitals and just say, okay, I'm just going to bond with these guys, and I'm happy. Okay, so we're knocking down walls in a house to make a new space called sp. I got 1 electron in each. They're the same energy. And I can make a bond, one with each unpaired electron, for a total of 2 bonds. And this helps us explain why we don't care about the octet rule anymore, because we're blending orbitals. Okay, our next type of hybridization is, we're going to do this next, sorry. Let's look at the shape of the sp orbital. Sorry, I got ahead of myself for a moment. Now, if I mix 1s and 1p, he's going to look like this. He's going to be slightly rounded with some of that S character, and he's also going to be a little bit of bow-shaped because he's going to have some P character in there too. And then when you overlap these 2 sp orbitals, it looks like this. Kind of like a p orbital, but they're bigger and rounder. We knocked down some walls in our house to make a new shaped orbital. Now I've got 2 places where I can put an unpaired electron, and now we're open for business. We can do some bonding and make a molecule. Okay, so if you have these 2 sp orbitals, what shape will they make? Well, the farthest apart they can get from each other is 180 degrees. And that is consistent with what's observed with beryllium difluoride. This is a linear molecule. Okay, they all form a line. So this will happen every time. If you have sp orbitals, you will have a linear shape. So what if we have 3 electron domains? Let's take the example of boron. Again, we're explaining why we're breaking the octet rule. Boron has an additional electron than beryllium. So I'm going to mix 1s and 2p. So I'm mixing these 3 orbitals to make 3 new hybrids. And they're going to look like this when I blend them together. they're going to be vaguely P-shaped, but they're going to have some rounded character as well, because you got some of the S influence in there. And these are degenerate orbitals, meaning they all have the same energy. So what boron's going to do, he'll stick one electron in each lobe, and now we've got 3 electrons open for business to make bonds. So if I have this trigonoplanar arrangement for my sp2, I don't need to obey the octet rule anymore. I blended my orbitals to make new ones, and now I can make a molecule with 3 bonds. And I'm fine with that. Very stable and happy, no problems. So if you have an sp2 hybridization, you will get a trigonoplanar molecule. So let's say now we have carbon. Carbon will do sp3 hybridization because we're adding another electron on there. So what carbon will do, he'll put an electron in S, one in one P, one in the other P, and one in the third P. Because remember, carbon has 4 valence electrons. So he's going to promote his electrons, so there's one in each, and he's going to blend these guys together to make sp3 orbitals. And that gives me that tetrahedral arrangement, 109.5 degree bond angle. So if you have sp3 hybridization, you're blending one S in all 3 of your p orbitals. You're going to get sp3, and you get a tetrahedral shape. So here, let's take the example of water. On our central atom, which is oxygen, he has 2 bonds and 2 lone pair. He's going to have sp3 hybridization. He's going to hybridize all 3 p orbitals with the S to make these new bubbly shapes, bigger, more rounded. And 2 electrons will be in the bonds, and there's going to be a pair of electron in each sp3 orbital over here. So 2 of the sp3 orbitals are bonds, are used for bonds, and 2 are used for the lone pair electrons. All right. So to figure out what your hybridization is, the first place to start is always draw your Lewis structure. So you need to know how many lone pair you have and how many bonds you have on your central atom. Once you've got your Lewis structure, you can get your shape. And then you say, okay, what hybridization do I need to get that shape? sp3 for tetrahedral, sp2 for trigonoplanar, sp for linear. Okay? So this is a summary and some examples. So if I'm going to blend an S and one P, I get 2 sp orbitals, and I get a linear molecule. And here's some examples of that: beryllium difluoride and mercury 2-chloride. If I want to blend one S and 2 of my p orbitals, I have sp2 hybridization, and I have a trigonoplanar molecule. So that would be some examples of this are boron trifluoride and sulfur trioxide. We'll do this. If I want to blend all 3 p orbitals with the S to make sp3, I have a tetrahedral arrangement. And my examples here: methane, ammonia, water, the ammonium ion will take this shape. This would be the electron group geometry for all these 3 guys. All right, so this is great, but what if I have a double bond? Now what do I do? Well, we hybridize a different way for multiple bonds, because we need to be able to accommodate the fact that we do observe double and triple bonds. But what if we leave one of our p orbitals or 2 of my p orbitals non-hybridized? Then they're available for double and triple bonds. So there's 2 ways you can have your orbital overlap that we talked about earlier with the valence bond theory. You can have sigma overlap, where you have head-on overlap, or you have a pi bond, which is sideways overlap. And you have pi bonds for your double and triple bonds. And sigma bonds are used for all your single bonds. So here's an example of a sigma bond with head-on overlap. And you can draw a straight line through the bond and the nuclei of your atoms in the bond. That's your sigma bond. So all your single bonds are sigma bonds, head-to-head overlap, and they have a high electron density between the nuclei. Here's your pi bond, where you have sideways overlap of your p orbitals. You will do this with p orbitals that have not been hybridized. They can have this sideways overlap. That's called your pi bond. You get the pi bond for your double bonds and your triple bonds. And your electron density is above and below the nuclei in your bond. So single bonds are always sigma bonds. If you have multiple bonds, the first bond is a sigma and all the other are pi. So if you have a triple bond, you'll have one sigma and two pi bonds present. So now let's go into some hybridization for when we break the octet rule. If your central atom has 5 electron groups, you're going to hybridize one of those d orbitals along with the 3p and the 1s. And now you have 5 sp3d hybrids. These are all equal in energy and all available for bonding. These ones that are not hybridized, we're going to leave them alone. We don't need them. Those are unused rooms in our house. We're going to use these guys. Now I've got 5 locations where I can make a bond. And that gives me my trigonal bipyramidal shape. So if you have a trigonal bipyramidal shape, that means you have sp3d hybridization. We're blending one of those 3d orbitals into my hybrid. I'm knocking down extra walls in my house because I need more space. So here's an example of a molecule with sp3d hybridization. This is arsenic pentafluoride. I have my central atom here, arsenic, and I've got him surrounded by 5 fluorines. This is how I represent him as a Lewis structure, but this doesn't really help me visualize it in 3D. This guy does. And this guy here shows me my hybridization scheme. The arsenic has sp3d hybridization. If you're the outermost atom, you don't need to hybridize. It's just your outer electron is in p and you call it good. And here's our shared space where our bond exists. So in the bond, we have from one end sp3d orbital, and from the F, it's just a p orbital overlapping. This gives us our shape. So we start here to know how many electron groups we have, and then we end up here. This is what we look like in 3 dimensions. Alright, so for octahedral geometries, again, we're breaking the octet rule. If our central atom has 6 electron groups, now we need to grab 2 of those d orbitals instead of just 1. And we're going to mix him. And now we've got 6 hybrids that are all equal in energy and all open for business. So I can stick 1 electron in each one of these, and now they're all available for bonding. So if I mix 6 orbitals, I get 6 hybrids. So I'm mixing 1s, 3 of the p, and 2 of the d, get a total of 6 hybrid orbitals. They are sp3d2 hybrid orbitals, and that gets me my octahedral arrangement. We can also use some unhybridized d orbitals to make pi bonds as well, but now we're getting a little exotic. That's outside the scope of this class, so don't worry about that part. So here's an example of a molecule with sp3d2 hybridization. Here's our starting point, drawing the Lewis structure. We're breaking the octet rule. I've got 6 fluorines on my central sulfur. This is okay. He's totally stable, very inert, very unreactive gas, sulfur hexafluoride. It's used actually in air quality field projects to help as a tracer to see where your wind is going. In any case, it's very stable, very inert. He's very content with this hybridization. Okay, he's not reactive at all. So on the sulfur, I have the hybridization sp3d2. So I grab 2 of those d orbitals to make hybrids. I knock down more walls from my house to make new rooms. And he's overlapping with a p orbital on each of my fluorines. So this gives me my octahedral shape. So I have 6 hybrid orbitals, all open for business, all available for bonding. And so fluorine comes along and says, okay, I'll fill up all your rooms. Here we are, very stable. All right, so these hybridization schemes go with electron group geometry. So if you have 2 electron groups on your central atom, sorry, you have a linear geometry for electron groups, not necessarily molecular, but just electron geometry. Linear, and then your hybridization scheme is sp. I only hybridized 1 p orbital with the s to make that guy. If I have 3 electron groups, my electron group geometry is trigonoplanar. My hybridization scheme is sp2, and I look like that. 4 electron groups, my electron group geometry is tetrahedral. I have sp3 hybridization. 5 electron groups, trigonal bipyramidal, sp3d hybridization. There's my shape. And 6 electron groups, I have an octahedral shape. My hybridization is sp3d2. And I'll run through these examples and how to do these in the next lecture. Okay, so we talked about in the previous chapter about resonance, where the connections in your atoms and your molecules stay the same, but the double bond can move around. If we have resonance, those electrons that can move around, those are called delocalized electrons. They're not confined between 2 atoms. They can wander around the whole molecule. And benzene is a good example of this, and this is how we can visualize this with our sigma and pi bonds. So here's benzene. It's a 6-membered carbon ring. I got a hydrogen hanging off each carbon. All the first bonds are sigma, but all the double bonds are pi. So he's going to have his p orbitals like so, and then they'll start to overlap. If they were localized pi bonds, they would stay like this, but benzene has resonance. So you have electrons wandering all around the ring. Okay, and this gives you extra stability in your molecule. If those electrons can get smeared around the ring, you have extra stability. All right, so I'm going to stop here, and my next video will be covering the examples in Chapter 11, 11.1 to 11.7. Okay, if you have any questions on this lecture, you can either email me or you can use the comments below. All right, thank you. Sorry about the coughing.